right, section 4.3, arithmetic. In Hindu Arabic. Hindu Arabic, what's that? Our numbers. All right, good deal. So the first thing we're going to take a look at is expanded form. Expanded form is a form in which the value of the digits in each position is made clear, thinking of 942 as 9 times 100, 4 times 10, and 2 times 1. That should look familiar because we've been doing it with other base systems in the last section, right? We didn't stop there. We would simplify it then from there. But that's what we were doing. We were writing theirs in expanded form. All right, so for fun, first one we're going to do, how would I write the number 12,398 in expanded form? Not quite. How about 1 times 10,000? Is that okay, Garrett?
Yeah.
All right, then what am I going to do with the 2? 2 times 1,000. And then what am I going to do with the 3? 3 times 100. And then I've got a 9. 9 times 10. And 8 times 1. The next thing you do, after you've written it out like this, is you write it in powers of 10. Okay, so you might think, well, how do I know what the power of 10 is? And here's the cool thing. The power of 10 is just the number of zeros you have. So how many zeros do you have in 10,000? 4. So this is 10 to the 4th. Write yourself a note down. That's how you know. It's the easiest way to deal with it. It's the number of zeros. How about 1,000? 3 zeros, right? 10 cubed. And 100? 10 squared. 10? 10 to the 1, right? There's 1 0, 10 to the 1. How could I write the number 1 as 10 to a power? It's 0 power. Okay, that doesn't look like a very good 0. Let's try it one more time. That's not bad. So this is 10 to the 0.
I can just do it like this.
Okay, we'll look at it afterwards, Leah. If you want to do it different, we'll talk.
Fine.
All right, so the other thing we're asked to do, of course, is to go the other direction. Am I good to switch slides? Did everybody get that written down from before? Okay. So if you have the values 5 times 10 to the 5th plus 0 times 10 to the 4th plus 3 times 10 to the 3rd and so on, if you have this one written down, what number is this? There's no funny symbols or anything.
503,568.
Awesome. Thank you, Trent. 503,568. Easy? Yeah, I mean, you're just reading the number that's times the 10 to make it in their value, right? Okay, so it's taking an expanded form and turning it into the condensed, simplified version that we have. All right, I'm going to show you another thing that seems to be oddly placed, but you'll see why it's placed here in a minute. We're going to look at a property of multiplication and addition, and it's called the distributive property. We're going to look at it perhaps backwards of what you're used to seeing it looked at. Normally you see the right-hand side where it says B plus C times A, and you see somebody distribute the A through, right? And you get what's on the left-hand side, which is B times A plus C times A. The distributive property. It's the same property even if you use it from the direction that this is written or if you use it from the direction you're used to seeing it. This property holds for all real numbers A, B, and C. And we're going to use that property for example 3. Okay. This says add or subtract, but it's the part after it that makes it unique. It add or subtract in expanded form. Okay? So the first thing we have to do is we have to put the numbers in expanded form. It's kind of like what was said when we were doing addition and subtraction in Egyptian. You add and subtract in Egyptian, and then you write the answer in our form. Okay? So how would I write 75 in expanded form?
7 times
So if you want to do 7 times 10 and 5 times 1, that's fine. Or if you want to do 7 times 10 to the first and 5 times 10 to the 0, that's fine. Either one are equivalent, and I'm okay with either one. You do have to have the 5 times 1 to represent the place value part. Okay, you can't just put plus 5. How would I write 34? 3 times 10 or 10 to the first, plus? 4 times 10 to the 0. Okay, 4 times 1 or 4 times 10 to the 0. So this is the other option. This is what Braden was saying. Okay, all good? All right, so the question is what happens next? Well, what happens next is we do addition just like we did always before. We start on the right and we add and we see what happens. So what happens when I have 5 plus 4? You get 9. You get 9 ones, right? I have $5 bills, 5 $1 bills in my pocket. You give me 4 $1 bills. Now I have 9 $1 bills. But then I also had 7 $10 bills in my pocket, and you give me 3 $10 bills because you're just so friendly. And then 7 and 10 would make 10 $10 bills. Legitimately, that is what you have, 10 $10 bills. But if your goal is to have the fewest number of bills possible, you do not keep 10 $10 bills in your pocket, do you? What do? Yeah, you turn it into a $100 bill, right? So you would have one $100 bill. How many tens? 0 $10 bills. And how many ones? Still 9. So your final answer in expanded form looks like that bottom line right there. 1 times 100, 0 times 10, 9 times 1. And if you want to write down what that is to make sure sort of what you're looking like, works if you added 75 and 35 out, standard notation, you can check and see, yes, this is 109 and it works. Okay, but the answer was down here. It was this last line right here. That's the solution. And it works the same way if you write it with the 10 to the 1s and 10 to the 0s. Any question on that? Okay, we're going to do the same kind of problem, but we're going to do it with subtraction now. 74 minus 48. Let me do it with the powers of 10 this time, just so that you can see that if you like that way to do it. How would I write 74 with powers of 10 in expanded form? Seven times 10 to the first plus 4 times 10 to the 0, right? And then I'm going to write down 48. So what's that going to look like? 4 times 10 to the first and perfect. But I'm not adding these this time. What am I doing? I'm subtracting. So if I subtract, I have to subtract both values, which means it changes what I had with the addition on that 8, because it really is 40 plus 8, right? I mean, that's what I have. But it needs to be subtracted from what was above. And I run into a problem, don't I? What's my problem? I need to borrow something, don't I? So I actually, in expanded form, am going to need another line of stuff to borrow. So what you need to borrow, let me read it, leave it in red, is you know that you need to take this 7, because you had 7 tens in your wallet, and you need to turn the 7 into a 6. So you need to turn one of your 10s into 10 ones, right? You're going to take a $10 bill and you're turning it into 10 $1 bills. Plus the 4 $1 bills that you already had, which is a total of 14. So you're going to write another line. It's going to look like this, but it actually, without the crossing out bit. 6 times 10 to the 1 plus 14 times 10 to the 0 minus 4 times 10 to the 1 minus 8 times 10 to the 0. And once you get it to here, you could actually subtract the 6 and the 4 first if you wanted to, instead of the 14 and the 8. It really wouldn't matter. We'll keep with our standard notation, which is to start on the right-hand side. 14 minus 8 is 6. So there's 6 times 10 to the 0. And then 6 minus 4 is 2. So there's 2 times 10 to the 1. And these are added together because this actually, in our number condensed form, would be the number 26. 2 10s and 6 1s in my mullet, I have $26.
Is it
Right.
added together because the two subtractions?
Well, it's added together because this is actually 14 minus 8, which is a positive 6.
Oh, yeah.
So that's what you're really seeing added, yeah.
And is the 4 changed to a 14 because the low side is a 10?
The 4 is changed to a 14 because when I borrowed over here, I borrowed one $10 bill, and a $10 bill turns into 10 $1 bills. So I have 10 $1 bills plus the original 4 $1 bills would be 14 $1 bills. Yeah. All right, we're going to change gears a little bit and look at another historical idea, which is an abacus. There's an abacus on page 172 of your book. I'm going to draw a version of one here in a minute too, but if you want to see one in your book, you can do that. This is one of the oldest methods for speed calculating. You have a bunch of beads on rods. That's what you have. There's a middle rod, and if your beads are pushed toward the middle, they're active. And if the beads are pushed away from the middle, they're inactive. You cannot remove the beads from the rods. I mean, this is a physical object. Okay, so there's no removing of beads. The beads are there, or they're not, they're there toward the middle, or they're not there, they're pushed away, but they're on the rods. Okay? Above the middle bar line, there's 1 bead, and below the middle bar line, there are 4 beads. The rods represent our place value system powers of 10, with the smallest power of 10 being on the right, so 10 to the 0, and the biggest power of 10 being on the left, maybe it's 10 to the 5th or something like that. Okay? So it looks like it's set up with our number system in mind, or at least a base 10 number system in mind. Yeah, I have one. The next page I have or next slide I have an example of what one looks like. All right, are you guys ready?
No.
Okay. Carrot, are we good to switch? Still working?
Okay.
All right, everybody else good too? Okay. Here's a picture of an abacus. So let me describe what you're seeing here. You're seeing the rod in the middle, okay? So imagine that what this would actually look like is it would usually be done in wood. So the bottom part, the side part, and the top part would all be wood. The one rod in the middle would be metal, okay? Each of these rods here are also metal, and there's beads that slide along them, okay? And you're going to work with this at your desk, if you will, flat, so that the beads don't slide unless you make them slide. So gravity's not going to push them somewhere, all right? If they are pushed toward the middle, they count. They're part of your answer or your number. If they're pushed away, either to the top or to the bottom, they're not counted. But you'll notice that every rod, or I should say, above the middle rod on the top part, there is 1 bead on every rod. Not more than 1. 1 and only 1. Okay? And below the middle rod, there's 4 beads on each rod. So when you draw pictures of these, yours have to have those characteristics too. So you're physically not, adding or subtracting any dot or any beads, because physically this is an object that you couldn't have done that with. Does that make sense? This isn't really just a picture. This is a picture representation of a real thing. So if you're taking a look, these are powers of 10 as well. This is 10 to the 10 to the 0, and then 10 to the 1. 10 squared, 10 cubed, and 10 to the 4th on this particular abacus. And what these are really is just our place values, right? So I should be able to look at the rods and just write down what numbers on that rod in that place value, whether it's 5 or 10 or not 10, 5 or 8 or 9 or 0, and I should be able to put them down. So we're going to do that. We'll start on, it doesn't really matter where we start. We'll start on the left. On this left-hand side, notice there's nothing pushed toward the middle, right? No beads are beside that middle rod, so this would be the number 0. Again, the second one, no beads towards the middle rod, so it's another number 0. So far, not interesting, right? Next, I actually have 2 of the bottom beads pushed toward the rod. Bottom beads are worth 1, top beads are worth 5. So if I have 2 beads from the bottom pushed toward the rod, what number is this? 2. Next rod, I have 1 bead from the top pushed down. I have no beads from the bottom pushed up. What number is this? 5, because top beads are worth 5. And then on the last one, I have 1 bead pushed down toward the middle from the top and 1 from the bottom. So this is the number 6. So this would be the representation for the number 256. And you don't have to, if they've already drawn the abacus for you, you don't have to redraw that on your homework. I don't need to see the picture again. Now, some of them are going to ask you to draw an abacus, though, like our next problem. So on our next one, we've got the number 70,163, and we are going to draw an abacus that will represent this. So when we draw our abacus, we are going to draw an abacus that has the same features as the one we just looked at. It's going to have a middle bar, and it's going to have vertical bars coming down. 1, 2. This particular number has 5 digits, so you at least need to draw me in 5 of these bars. All right, my bars are not looking so good. They make it look a little bit open-ended on the left when they draw theirs, so that's what I'm trying to do as well, because you could have a particular abacus having been a bigger abacus that you had, in your possession or something. All right, how would I get the number? We're just going to go from left to right because it doesn't matter where we go if we've got the number of bars in place. I drew 5 vertical bars because this over here on the far right, this isn't the bar. This is the edge of the piece of wood. Okay, so I drew 5 vertical rods. How do I get the number 7? Okay. Now, this is the active beads, but I have to draw the other beads that are on this particular rod that are inactive. Where else do I have beads? 2 at the bottom. Good. Because on the bottom, there's always 4 beads. Yeah. And on the top, there's always 1, so I don't need to draw any additional one on the top. The next number is the number 0, so what do? Right, 4 beads are going to go on bottom and 1 on top. None of them are active, so none of them are near the middle bar. How about the number 1? Just 1 from the bottom that's pushed here, right? And then the one above the middle bar goes to the top. How many go at the bottom of below the middle bar? 3 more. How about the number 6?
1 on top, 1 right below it, 3 on bottom.
Perfect. Okay, so the active beads are a 5 from top and a 1 from bottom. And the number 3? 3 active beads on bottom pushed toward the middle, with 1 more inactive pushed all the way to the bottom, right? Because there's got to be 4 there. And then what else? 1 inactive at the very top. So far, so good? That's what you're going to be doing with the abacus. Okay? You're going to be drawing representations and interpreting representations. One last topic in this section is lattice multiplication. This is the lattice method for multiplying. And the description here is something like this. You're going to create rows and columns for your digits. You're going to divide each box, compute each product, and add on diagonals. So write those down, and then I'll show you what all that says that you're really going to do. And we'll do 2 examples. And then I'll apologize in advance that we're not going to do group work in class. It'll just be part of your homework. But everything in my math lab will be finished. So you can do everything in my math lab by Saturday at midnight so that you've got your whole spring break to not do any real homework for math. That part's good, right? Yeah. I don't want you to wait till next Saturday and have forgotten everything. Just get it done and over with, and you don't have to do anything else in math. All right. We're going to do the number 23, and it doesn't matter whether I write the 23 as 2 and 3 on top or 2 and 3 on the right. But one of them is going to go separated a little bit distance apart on the top. The other one's going to go separated a little bit of distance apart on the right. Like this. Okay? So the numbers we're multiplying are always going to go along the top and along the right. Do not put them anywhere else, or they're going to run into other things that you're not going to have space for. Next thing you're going to do is you're going to create a box. Your box needs to have, in this case, a column for each of the numbers 2 and 3, and a row for each of the numbers 1, 8, and 7. And if you put your 1, 8, and 7 on top and your 2 and your 3 vertically down on the right, then it means your box ends up being a different arrangement, but you still have the same rows and columns in a different spot. Okay? So there's 6 boxes, correct? Okay. This is problem number 1, where it says part number 1, where it says create rows and columns for your digits. Part 2 says divide each box, and this is what it means. You divide it diagonally. Okay, divide your boxes diagonally. So far, so good? That creates what's called the lattice. That's why it's looking like a lattice now, is because I've divided this. Step 3 here says compute each product. What that means is I'm going to do each of these 1-digit products, 1 digit times 1 digit. So I'm just going to start in the top right-hand corner over here. You can start where, I'm going to start in my top left-hand corner. You can start in any box you want. It doesn't matter. But I'm going to start right here. So this box right here is going to be 2 times 1, which is 2. And the 2 goes in the bottom corner of the box. Next box, I'm just going to go to the right. I'm going to go 3 times 1, which is 3, bottom corner of the box. Next, I'm going to do 2 times 8, which is 16. The 1 goes in the top corner. The 6 goes down in the bottom corner. 3 times 8.
24.
2 on top, 4 on bottom. 2 times 7. 14, 1 on top, 4 on bottom. 3 times 7?
21.
Sorry. 2 on top, 1 on bottom. All right. Okay, we did everything in step 3 now. Step 4, last step, is to add along the diagonals. Okay? So what we're going to do is we're going to take, let me do a different color here to make it clear.
So from right to left.
We are going to add from right to left. And these are my diagonals that you see. I'm drawing them again in purple here. On the next page, I'll have a bit bigger of a picture. But the bottom right here is my first diagonal, and it has just one number in it, so it doesn't really get added to anything. It just gets rewritten. It's the number 1. Down here, I've got 4 plus 2 plus 4, which is 10. I'm going to write a 0 down here, and I'm going to carry the 1 to the next diagonal. So now I've got a 1, a 3, a 2, a 6, a 1. 13 is right. So I'm going to write down the 3, and I'm going to carry the 1 to the next diagonal. I have a 1, a 2, and a 1, which is 4. The answer can be read right here. The answer is 4301. If you wanted to check this and you didn't have a back of the book, how could you check this? Just put in your calculator, right? Or just do it by hand the old-fashioned way, the way you remember from standard algorithm, right? The way you normally have done it before. You can check this yourself very easily. Agreed? Let's do the next one really quick. Notice, this one is 912 times 483, which means I want to have 3 rows and 3 columns because these are both 3-digit numbers. And again, it doesn't matter where you put them. You can put them wherever you'd like, top or right. So I'm just going to do 912 on top and 483 on the right. We're going to divide each box and multiply. 9 times 4. Okay, 36. 1 times 4. 2 times 4. 9 times 8.
You lost it.
Did it come back? Good. 9 times 8. 72. 1 times 8. 2 times 8. All right, 9 times 3. 27. 1 times 3. 2 times 3. Awesome. All right. Next we're going to add and we'll be finished, right? Bottom diagonal. 6 is 6. 6 plus 3 is 9. 8 plus 1 plus 8 plus 7. It is 24. Good job. There's a 2 and a full. I carried the 2 and I wrote down my 4. 2 plus 4 plus 2 plus 2. 10. Write down my 0 and carry my 1. 1 plus 6 plus 7. 14. Write a 4, carry a 1. 1 plus 3 is 4. So my solution, read along this side, right here, is 440496. Just out of curiosity, has anybody seen lattice multiplication before? This is taught in public schools now. So if you have nieces or nephews or at some point when you have children, you may encounter this at some point again. All right? The cool thing about this is that it separates the multiplication from the addition. Our algorithm has you multiplying and adding at the same time within the same step. This one does all the multiplication first. Just a second, Leah. Just a second, Leah. It does all of the multiplication first and all the addition second. So it kind of has a separation feature to it.